today's idea is if we can find area between curves, and we can rotate those around either the x-axis or the y-axis, we will get an area. So like, can you see that if I took this blue part and rotated 360 degrees around the x, it would make a disc that's the yellow? And if I added up all of those yellow discs together, I would get the bell. And adding up all of those yellow discs together will give me the volume of that bell. So we're going to look at volumes of different shapes using the calculus that we know, and we can find out volumes of all sorts of weird shapes as a result. It's called a solid of revolution, and we're going to rotate them either around the x-axis or y-axis, which is our axis of revolution. And we can either use a disk method or the washer method, and sometimes it's filled in completely. So here's the idea. What I said is those yellow parts is you would make an infinite amount of disks. And if you added all of those up, you would get the volume. And if you have two functions where it's area between them, those disks would look like a washer, and you could add all of those up to get the volume. And the formula is relatively amazing. If you have a solid disk and you're adding them all up, what is the shape of your disk? One of your disks is a perfect circle when you rotate it 360 degrees. What's the area of a circle? The area of a circle is pi r squared. The radius is just whatever your function is, f of x. And if we do the integral of the pi r squared from a to b, that will add up all of those disks and get you your perfect volume. The same thing with the washer method, but now you just have one disk minus the other disk. So you could do them separately, but what's really nice is using your integration rules and properties, you could combine those together, and then you just have the one squared minus the other one squared, and factor out the pi in front. Okay? And in the washer method, we sometimes talk about f as being the outer radius, and g of x as being the inner radius. Makes sense that you would take the bigger radius, subtract the smaller radius to get the washer. So sometimes you'll see this just written as big R squared minus little r squared. Did I scroll down too quick? Or are we good? Yeah, I'll let you finish.
Is the absolute line there meant to be there?
No, that absolute line was just my cursor. That when I took a picture of the page, the cursor was flashing, and I took it at the millisecond that it flashed on rather than flashed off. I can take out my whiteout pen. And take that away. I know, that's impressive. Okay. So here's some pictures. If you had x equals f of y, so now we have a function in terms of y, and we took this and rotated it around the y-axis, and made this that looks like a fancy hat. Although if I wore that, I'd only wear it if it was silver. And if you subtracted another function and rotated around, you see that it would make a whole bunch of washers, with an open circle in the middle, and that open circle would change all the way through. And if you added up all of those, you would find out the exact volume of that shape. So now, as long as we can create equations, we can subtract two graphs and have some weird shape in between, rotate it, and get all sorts of volumes. Which, like, the complexity of these shapes that are possible, it's like amazing that we can calculate. So if it's around the y-axis, it's the same idea as around the x-axis. And this is where it's sometimes nice to use the r² idea, because it's like, just what's my outer radius, what's my inner radius? Here's the picture. This, in purple, is my x cubed graph, right? I'm taking the part from 1 to 2. So that would go up to 1, 1, and all the way up here to 2, 8. And if I rotated that around, it would go down to 1, -1, and here would make a perfect circle. And it would rotate down to 2, -8. And I find for drawing these, maybe I should just, would you like to see me draw it right from the beginning? Because sometimes it's already drawn. Gets a little bit confusing. So, if I were drawing this, there's my x-axis, I've got my x cubed graph, I've labeled the points 1, 1, and 2, 8. So significantly underneath, if I rotated this around, I'm going to have 1, -1, and rotating this all the way down here is going to give me 2, -8. Take those 2 points that I have, and then I like to imagine the dotted line. I draw a little circle there, and oval. Draw a circle there. And if this was reflected down, that would match up with that. How I like to draw these to visualize it best is I take my outside circle right here. Draw that. And I shade that in. I'll take out a crayon. I pick one color. And I shade that circle in. And then I take out a different color. Can you see that if you sort of have like this cone shaped thing with a circle here, there would be a circle here on this side as well. The blue is the outside part, and the green is the flat circle at the end. Just nice to visualize what shape am I figuring out here. But then I can calculate the volume of this because it's going to be the volume of all of the circles. What's my formula for circles? Pi r². So pi is out in front because you can factor it out as a common factor. R is my radius, and my radius is whatever my function is. In this case, it's x cubed. My radius is getting squared because pi r squared is a circle. So it becomes the integral from 1 to 2 of x to the 6 dx, easy to calculate. And you can plug these numbers in, and we can figure out that the total volume is 127 over 7 pi, whatever the units would be, cubed. Crazy, because that's a weird shape. So some things to notice in this question, you have to see which axes they're rotating about. Are they rotating over the x-axis or rotating over the y-axis? If they're rotating over the x-axis, then you're going to go from left to right. In this case, we go from 1 to 2 and figure out pi r squared from that. And then the r squared is whatever your function is. You would do exactly the same thing from y, except you'd go from a small value to a big value on your y-axis. So it's really no different for x and y, but we'll get to some examples that involve both. Okay, we'll do another easy one. Everybody good? Again, I'll draw it from scratch. I like this one. Looks like a half football, or maybe buying a big chunk of ham from the grocery store. I'll color it like a ham so you can get that vision. So I start by drawing x minus 1, which is a square root graph like this. We want to go from 1 to 5, so at 1 it's 1, 0, and at 5 it'd be 5, 2. If I imagine rotating this around the x-axis, then down here I would have 5, -2, and this, right, would go like that. And at this part here, I draw a little oval. Take out my crayons. I know coloring with crayons shouldn't be a very red ham. I'll make the, there we go. Ham bone in the middle there. So can you picture the cut part being the red part? That's why I like to shade it in a different color. Helps visualize the shape. Well, we could have made this, I could have gone green, I could have made it a watermelon. Oh, I feel like the part. Oh, now we got a watermelon. With an eye, it's like an eyeball, it's like some sort of a watermelon that's alive. Okay. And we want to find out, do we have enough watermelon to feed everybody? So we can figure out the volume of this watermelon. It's going to be a bunch of circles. And the beautiful thing here is that because it's a square root function, that's our radius. When you square it, that square root goes away. And it's a super easy integral to calculate because it just is x minus 1. And the rest of life is easy. You know what? I don't think you need to show any of that. Are you okay with not showing that? You could do that math, but I do need to go back up. There we go. Save you some time writing things down. I know you can plug in those numbers. You like killed that. You didn't mean to. Like a massive. I can only imagine what you do to that watermelon. I'm really happy with how the green and the orange are complementing. Like, very, very happy with that watermelon. I like the next question so much. Okay. Are we ready? Draw a cone with height of h and radius r. And that cone is already nicely drawn for you. Do you remember from grades 9 and 10 the formula for the volume of a cone? Do you remember it from, like, you had to do that with related rate questions, right? Yeah, you had to know this formula. What is it? 1/3. Pi r squared, because that was the circle at the bottom, times the height, pi r squared h. Fascinating. We now get to use integrals and calculus to make this formula. We're going to say, I forgot what the formula is, but I could draw this out. And I have a volume of revolution, because you see that you would add up all those circles right to the very end. But in order to do that, I'm going to need to know what this function is. Well, it's a straight line. Okay, that straight line, right, this line right here, if I write that as a function, it's a straight line, so it's y equals mx plus b. Can you see that your b is 0? And can you see that your slope, rise over run, is r over h? And so the r over h is what would go into your formula here. Okay? And I need to find the volume as I go from 0 all the way up to whatever h is. Well, this integral is not bad, because what do you do to an x squared? Add 1 to the exponent and divide. Look, that's where your 3 comes from on the bottom of your fraction. And the r squared over h are just any numbers, so you could bring them out in front as well. Oh my goodness. That's so cool. We just used volumes of revolution to make the formula for a volume of a cone. You could do this for a cylinder as well. Cylinder is really boring because the line is just flat. And cylinder is boring because it's just adding up the same circle all the way, so it's really not too crazy. So now you see where the 1/3 comes from. Most likely, haven't read up on my volumes of cones lately, but I'm quite certain that mathematicians thousands of years before calculus was officially created, discovered, however you want to actually you can verbalize or verb it, whatever verb you want to use. But ancient Greek would have known volumes of this. They would have figured this out much earlier. They were doing, Egyptians and their pyramids were figuring out all sorts of mathematical things way before calculus. But it's just kind of cool that now that we've got calculus, we can be like, hey, I wonder if I can revisit this. Is this possibly a lot easier a way to prove that it's a third compared to whatever methods were used prior to that? Most likely, yes. And now we have a very nice proof for it, right? In the past, proofs would be like, we'll build a cone, fill it full of water, we'll build a cylinder, we'll dump the water into a cylinder, and we notice that it takes exactly 3 to fill it up. So if my cylinder formula is pi r squared h, my cone has to be a third because it took me exactly 3 to fill it up. But that's kind of an observation, and you do it with a bunch of different cylinders and a bunch of different cones until you feel like, well, I've done it a bunch of different times, and it always seems to work, so therefore I feel that it should be 1/3. But now we're like, no, it has to be 1/3 based on the calculus. This is another good example. So, I like this example. I'm going to see how the picture is. I'll draw it again. I want to draw this. Okay? So, and now with 3D printers, you could probably even do this. You could print this out. I've always, okay, I could deal with plastic. I've always wanted to do this out of some very expensive metal like gold or titanium, but 3D printers don't print in gold, I don't think. I could deal with this in plastic. So if we took our cos graph and we took our sine graph, and the area in between them, right here, this area in green, that's the area in between those two. If that got rotated, so I'm going to take this dot exactly the same, I'm going to redraw that curve, and redraw this one, so that I have the green part again. Bring on it again. There we go. If this part was rotated, and I'm going to color that in blue crayon. If it was rotated all the way around, you see that this would all be green as a result. This part in here, I'm just going to lightly put some blue dots in here. I imagine this as building a beautiful dog water bowl for my dogs. And that, how nice would it be if I used a sine graph and a cosine graph? And it's actually, I've always imagined it getting custom made somewhere out of titanium or gold or some very expensive thing. So I haven't done it yet because it would be way, way too much money. But now with 3D printers, those equations would be super easy to put into a 3D printer. And I just think, wouldn't that be a cool looking water dish for my dogs? You might have to make sure there would be a tiny, tiny little, would there be a tiny hole that it would drip water out up there? I'm not sure. Where the printer would probably fill that in. But you could be like, I designed, that would be like super math geeky. People would come over, oh, that's a weird dog. Well, yes. I designed it by doing a volume of revolution of a sine curve and a cos curve, and they'd be like, okay, we're going home. We don't need to visit with these people anymore. But I don't know. I think that'd be, I'm going to have to go down. I'm going to see if I can get it built. Now, yeah. How much plastic do I need though? I'm gonna go down to the 3D printer downstairs and get this built. And they're gonna be like, no, that uses way too much plastic. Oh, can you make it a little smaller? Bigger? Let's see. Well, what you would have to do is volume of revolution of the area in between, which the upper curve is coast, the smaller curve is sine, and I'd have to subtract them. And this is looking like advanced techniques of integration. Doesn't it feel like it's going to get there? Because it has like a cos squared and a sine squared, and you guys are having nightmares about that already? From all of your pre-tests and take-home quizzes? Whew. So you could either, like some of you did cos squared on its own and use the double angle formula to figure that out.
Hi, excuse me, do you have Scott Grass?
Yeah.
Can you send him to the office for a brief, pick something up?
All right, I'll be right there. A brief pick something up, right? We're back on it. So you could do the integral of each of them separately, and you could do them using your double angle formulas. But if you have cos squared minus sine squared, you might notice that that is also one of your double angle formulas, and you could switch it to that right away. And then the integral is easy because going backwards from cos would have to be sine, so it would be sine 2x, but you'd have a chain rule, so we have to divide by 2. And I need pi over 2 units cubed. So it depends how big of a dog dish I want it. Like this is 1 unit. So what? Because cos goes up 1 unit. So it depends on what unit I want to have it go up. I want to make it, that 1 unit, 1 foot, that'd be like one big dog dish. Make it drink water for a long time. That might take too much. Because a 1 foot would be like a 2 foot diameter. That might not be big enough. That might be too big. So I'll have to decide. Whatever unit I do, I'm going to have pi over 2 unit cubes of those. I don't know how much plastic that's going to take. But I think it should be definitely doable. So now we're going to see a question, what's the difference about going about the x-axis and going about the y-axis? Everybody good? Okay. So now we're going to look at the same question about the x-axis and then about the y-axis and how that is different. We have 2 graphs. We have the cube root of x and x squared. So if we were going about the x-axis, the cube root of x is your bigger radius, and your x squared would be your smaller radius. And we're going to take this shape and flip it around the x-axis. Now your volume of revolution will go from an x value of 0 to an x value of 1, because if you set up where those 2 equations were equal to each other, they're equal to each other at 0, 0, and 1, 1. So the idea is we need to find A and B, where they intersect, already from the graph. Yes?
Were we not rotating it around the x-axis before?
We were before, yeah. But this question we're going to do both the x-axis and then part B we're going to do the y-axis.
Oh.
Just to see how the same question can be asked in 2 different ways. So my outer radius is the x to the 1/3. My inner radius is the x squared. And it's going to be pi r squared for both of them, so both of them are going to get squared. And now these are easy integrals to do. And if you plug it in, you're going to get 2/5 pi, and whatever units you have would be cubed. And all of our questions so far have been about the x-axis, so we're getting used to that. And that's more typical because you're used to functions being written y equals x to the something. Okay. If we do this same question around the y-axis, we're going to have to change all of our equations. Instead of y equals something, we want x equals something. But I'll wait, make sure everybody's ready. Everybody good? All right, almost? Not quite? Okay. So now can you see that your bigger radius is this blue dot, and your smaller radius is the green dot? And we're going to take both of these equations and rewrite them. Okay? So when rewriting them, what would I have to do to get x by itself? On the 1, I would have to cube both sides. So I get x equals y cubed. That is this green equation there. And how would I get x by itself with the other one? I'd have to square root both sides. And when I square root both sides, that's the blue dot. Now technically that would be plus or minus a square root. But can you see that we only have the positive side on the right? So again, the volume is always bigger radius squared minus smaller radius squared, because it's big circle minus small circle. The pi can get pulled out. We need to find out what values it goes from, C to D. So now we're looking at the y coordinates. This is actually, part of me says, oh, too bad I picked this example where the x coordinates and the y coordinates are identical, because it doesn't really make it different. But now you would look at 0 to 1 because those are the y coordinates. Whereas before we looked at 0 to 1 because those were the x coordinates. It's kind of too bad that the numbers are the same. And when you square these, is it the same volume as the other shape? No. Because this time we're going about the y-axis. Last time we were going about the x-axis. I don't think these would make as good water bowls. They don't look like. In fact, the bottom wouldn't be flat. My one dog would get scared of it, because it would move while drinking the water. Yeah. So anytime you're going about the y-axis, again, if you think of the big radius minus a small radius, it's a nice way of saying it's the same whether x or y. But if I'm dealing with y, then I need all my equations to be x equals in terms of y. If I'm around the x-axis, then I can have y equals in terms of x. And this idea of the radiuses, thinking in terms of radiuses is nice, because now we're going to play around with not just necessarily rotating around the x-axis and y-axis. What if I move those numbers? I can move it. Oh, let's rotate around y equals -2. Could we still do this? What would that look like? So that's our next idea here. If we take lines parallel to the axis, and then of course mathematicians play around with it, so like, well, why don't I rotate it over diagonal lines? We don't go to that, but you could. You could rotate something over a diagonal line. That creates a whole nother kind of mathematical problem to try to think about and solve. It's not crazy hard, but it is harder. But let's just start with changing things to being parallel. Okay, so here we're doing a solid of revolution generated by revolving the region bound by the graph of y equals the square root of x from x equals 0 to 4 and the line y equals -3. I feel like drawing a picture. This is like a watermelon on steroids. Nice. Okay, so here is my square root graph, just like that. We're going from 0 to 4, so that would be 0, 0, and at 4, I'd have the point 4, 2. But I'm not revolving it around my normal x-axis. I'm going down to the line y equals -3, and that part is getting flipped over. Can you see if I took this and did a 180, it'd be 1, 2, 3 here would be this point, and this is 4, 2 is technically 5 away, so I would be, I need to move this down. Whoa. There we go. 5 away would be right about here. At 4, negative, what number would be there? This is already at 6 here, right? This is at 0, -6 here. 4, -8. And, right, there's our watermelon on steroids. I would like that color coding I did last time. Just going to add some orange underneath and then do the green. Oh. There's the evil eye of the watermelon monster. Or maybe this is just a watermelon that's been cut twice. That's a possibility. Maybe there's watermelon blood oozing out of the side. I don't know. Okay, that took a really dark turn. I'm sorry. Okay, so we have this shape. Again, we need to figure out what this radius is. There's no washer here. It's just a disk. We just need to see what that outer radius is. Well, that outer radius will always be this distance of 3 plus my square root graph. So when I write it out, it's just my square root graph, but now I've added an extra 3 to it. If I square that, then you have to multiply that out, and each of those integrals are actually not hard to do. And the area of our bloody watermelon is 76 pi units cubed. Trying to think of what I could make you believe. Do watermelons actually bleed? Trying to think if I could make you believe that inside watermelons are actually white until you cut them open, and then when it hits oxygen, it turns them red. You could never prove that, because every time you cut it open, it's like, oh, it's already red, well, it hit the oxygen. It was white before. I think I could convince high school students to believe that. You'll go home. What did you learn in school today? Mr. JR is plotting to destroy young minds. My y-axis actually looks like stitches after the cut. Okay. So let's draw this picture. It's an x equals y squared plus 5 graph. And we've got line y equals -1. So -1, right? If you're like me and you have this, and you have the choice between graphing y equals -1 or x equals y squared plus 5, I think you'd probably be like me and like, I'll go with the y equals -1 horizontal line first. How do you graph x equals y squared plus 5? That's a horizontal parabola. Can you see that if you plugged in 0 for y, you would get 5 for x? So our parabola looks like this. And we want to go from -1, y equals -1, all the way up to 3, 1, 2, 3. Take this part and rotate it about the line x equals, -1 to 3, y equals -1, sorry, drew that wrong. I drew it all wrong. I thought, here, I'll start with the part that's easiest, and then I draw it wrong. Nice, that's going to be on the video. Y equals -1 up to 3, and about the line x equals 3, so 1, 2, 3, that's this line right here. I'll draw it in red. So we're taking this part colored in here, in purple, and we're rotating it around here, making a shape something like that as our volume. That's our visual. Now again, what do we need? We need this radius. How are we going to calculate that radius? Well, if we went all the way back to the y-axis, it's y squared plus 5. Do you see that you would need to do the y squared plus 5, but then you're taking away 3 from the radius? Because it's not all the way back to the y-axis, we have 3 less as a result, which then just becomes y squared plus 2, and now we could set this up, square it, multiply it out. Once you've got the idea, the rest of it is just simple algebra. Okay. First of all, we're revolving the region bounded by the graphs of 2x and x squared. So this first picture here shows you the 2x line in red and the x squared line in blue. And we have this thin little yellow part in between. Now we're going to rotate that around y equals -5. Can you see that that would increase your radiuses by 5? So now our outer radius, our big R, will be the 2x one. Our little r will be the blue one, the x squared. But both of them are going to be increased by 5. That will make a washer. So now we just need, and of course, with those two graphs, you'd find out where they intersect, which is 0, 0, and 2, 4. So we want to go from 0 to 2. The bigger radius is going to be the 2x plus 5, because you added 5 to your radius by rotating it down here. And your little radius is the x squared. It's also plus 5. Those both get squared, so our plus 5s don't just cancel each other out. You actually have to multiply these things out and simplify. And the integral is easy. The plugging in isn't bad. And notice that we have the pi out in front. You could multiply that out to get an actual number, but we may as well just keep it as an exact answer in terms of pi. And I'm going to give you the last one to try on your own. We do the shell method, then we do cross sections. Oh. And I know Rourke was complaining that he was sort of in between not having a take-home quiz. So, oh my goodness. Okay.
I just want to remind everybody that
here we go.
Monday is a big Jets game, so make sure you are wearing white on Monday.
Woo!
White out on Monday just to help our Jets. Go Jets, go! Have a great long weekend, everybody.
We shun anyone who doesn't wear white on Monday.
Did you get?
At the very least, has to be a Jets jersey. It should be white, bare minimum.
Now your outer radius is going to be 2 minus the function.